All right, so let's review. So the electrical potential is a scalar field created by an electric charge. So we spent many chapters talking about the fact that an electrical charge creates an E field, and that's one way of looking at it. We're looking at it a different way. So here we have a V field, a scalar field. The electric field is related to force. The V field is related to electrical potential energy. So here's a definition of the V field, or the electrical potential. Same thing. The potential is equal to the electrical potential energy divided by the probe. In the units, energy is joules, charge is coulombs, a joule per coulomb is a volt. Here's a battery. So a battery is a source of potential, although I just like to think of it as a source of energy. I mean, because, they're related. So, and this is back to our conventional current, where we're assuming that the current is the motion of positive charge carriers. So here's the negative terminal, here's the positive terminal. The positive charge carriers want to be here. So we'll say that's potential energy equal to 0. Now to make this thing a source of volts or energy, we need to give these positive charge carriers energy. So there's a chemical process in the battery that basically separates charge. So let's just assume that the positive charge carriers, that they're pushed up here where they don't want to be. So they've gained potential energy. So here they are with potential energy. What are they going to do next? Well, they want to go back to the 0 point. So they're going to travel through this wire. Oh, then here's a light bulb. They're going to give off their energy to the light bulb and then continue on their merry way. So the light bulb doesn't eat positive charge carriers, or in the real world, the light bulb doesn't eat electrons. It just uses up the energy of the charge carriers. So 0 volts, 6 volts. All right, that's the review. Now, let's look at this equation here. So again, this is the definition. V equals UE over Q, where this is the probe. Okay, so let's say we have some region where there's a potential, a V field set up. And then let's just say we put some charge there. What is the charge going to have? Not feel, but have. It's going to have electrical potential energy. Well, what's the equation? UE equals QV. So that's the energy that this charge has in this potential field. So that kind of brings up the subject of energy. So in Physics 121, we spent a long time talking about energy conservation. So let's assume that we don't have any friction, so mechanical energy is conserved. Well, 121, K initial plus U initial equals K final plus U final. Now, for 121, this could be spring or gravity. But now we have the possibility of electrical potential energy. So let's forget about the spring. And so this is what we have. So initial kinetic, initial gravitational potential, initial electrical potential energy, kinetic energy, gravitational potential energy, electrical potential energy. Now let's make this simple. Let's just say if we have a wire, it's horizontal. So Y initial equals Y final. So we can just get rid of those two terms. So there you go. All right, so if everybody could please, so pause the video, read this problem, and solve for it. Solve for the final velocity. Okay, let's solve it. So the initial velocity is 0. The initial potential is 0, so this is all 0. So we have 0 equals 1/2 mv final squared plus q v final. We want to get v final, so put that over the other side and solve. So V final equals minus 2Q V final over M square root. So you just plug in your answers and you get, I don't remember, I think it was like 1.2 times 10 to the 8th meters per second. So there you go. Energy conservation with electricity. Okay, let's talk about capacitors again. I'm sorry. What the heck? Here we go. All right. Capacitors. We discussed this already, that if you have a charge in here, the potential energy is QES. This is the definition of voltage. It's energy over charge. So let's figure out the voltage for a capacitor. So V equals UE over Q. So it's QES over the Q. The Q's go away, so we just get ES. So that's the electrical potential energy that a charge would have inside a capacitor. Because one important thing here, so S is always defined to be 0 at the negative plate. And this is a positive number, right? Just because it goes to the left doesn't, it's a positive number, right? So don't forget that. S is always 0 at the negative plate. Okay, let's talk about it and see if this makes a bit of sense. So let's say that we have a positive charge inside the capacitor. Okay, so let's do this. UE equals QES. Let's take a positive charge. So where does a positive charge want to be? Here. So that would be a small amount of potential energy. Where does a positive charge not want to be? Here. So that would be a large amount of potential energy. Now let's use the formula. If the positive charge were here, S would be 0, so UE would be 0. So U minimum, let me find it here. U minimum would be 0. Maximum potential energy would have the positive charge here where it doesn't want to be. So U max would be QES. Let's do a negative charge. It's a little different. Okay, where does a negative charge want to be? A negative charge wants to be here. So that would be the minimum. Well, let's do it differently. Where does a negative charge not want to be? Where does it have the most potential energy? Well, next to the negative plate. Okay, according to the formula, what's the potential energy here? 0. Wow, that's weird. So U max equals 0 for a negative. Okay, where does a negative charge where does a negative charge want to be? Here. Okay, let's plug it in the formula. For a negative charge, this is negative, so we'd have negative, let's say E or QES. So U minimum would be minus QES. All right, so it's kind of strange sometimes maybe thinking at the maximum is 0, but it makes perfectly sense, right? Good sense because this is negative. Okay. All right, let's talk about okay, so I just showed you a few minutes ago that the potential inside a capacitor is the constant E field times the distance from the negative charge. So here's a nice example. Let's say we have this connected to a power supply or a battery. So this is 1.5 volts and this is 0. So look at, we have a constant E field to the right the voltage equals that constant E field times the distance from the negative plate. So we can see that everywhere along this green dotted line, the potential is 0.3 volts. 0.6, 0.9, 1.2. So these lines are important because the potential is the same everywhere. So those lines are called equipotential lines. And because equi means equal, right? So everywhere along those dotted lines, the potential is the same. Now, this is kind of interesting. So this means that, I don't need to have a charge in here. As long as the plates are charged, the potential exists anywhere inside the capacitor. And we're going to use that when we do electrical circuits later on. And you're going to study this in the next lab. Okay. Yeah, this is how, okay, so the formula, according to the textbook, is V equals ES, because Randy Knight likes the variable S for the distance from the negative plate. Well, when I was a little kid, there was a TV show. It was called Mr. Ed. So Mr. Ed was a talking horse. But what was funny about it, so the horse lived with a family, but the only person who could hear and talk to the horse was the husband. Nobody else could hear or talk to the horse. So the husband, he'd be talking to the horse, and then his wife would come in, and she wouldn't see the horse, and she'd say, "Who are you talking to?" And he would sort of just mumble something. But anyway, it was a really funny show. So I don't remember ES, I remember ED, because then I just have to remember Mr. Ed. So it just makes it easier for me. But anyway, you can use whatever you want. So this is what you're going to be doing in lab. So you're going to have a pan of, like a glass pan. You can put a little bit of water in it. This is going to be a conductor, just a piece of metal. This is going to be a conductor. You're going to connect the conductors to the power supply. So this is going to be 12 volts. It's going to be 0. And then you're going to use a voltmeter to determine those equipotential lines. Now, this is like a point charge. This is like a plate. So near the plate, you should expect it to be constant. Near a point charge, you should expect it to be circular. But you can see what happens when you're between the point and the plate. It kind of goes like that. Okay. And so these are these equipotential lines. And you can see, and then the E field is perpendicular to the equipotential lines. So these are the E field lines. And just as we talked about in class, the E field goes from positive to negative, or you can say high voltage to low voltage, or high potential to low potential. So you'll do this with 3 different geometries. Okay. So here's another example, 100 volts, 0 volts, 0 volts, minus 100 volts, 50, minus 50. And you have these equipotential lines. All right. Okay. And okay, let's say we didn't have this battery. Let's just say we had an uncharged plate and an uncharged plate. So and then all of a sudden we connect the battery. Well, if the battery is 1.5, well, I mean, you can, if the battery is 1.5 volts, there's going to be the charges are going to move, and then they're going to fill up the capacitor, and so the delta V of the capacitor will be 1.5 volts. In fact, so initially, if this is uncharged and this is uncharged, the charge is going to move. And they're going to move until the potential is equal to 1.5 volts. After the potential here equals the potential there, the current will stop, and you'll just have a charged capacitor. Yeah, this just shows that, again, all we ever care about is the change in potential. So we can always call our 0 point whatever we feel like. So we can see here, the delta V is 50, delta V is 50, delta V is 50. Even so, look, we had 100, 0, 0, minus 100, 50, minus 50. But the delta V is always the same, because that's the only thing that's physically significant, the delta V. Oh, sorry. So let's figure out the voltage or the V field of a single point charge. You remember when we did E fields, the point charge was incredibly important. So we want to do the same thing for a potential. Okay, earlier we learned that U, E, for 2-point charges was K, Q, Q prime over R. I could have said Q1, Q2, whatever. Now the definition of V is UE over the probe. So that's just K, Q, Q prime over R divided by the probe. So the probes cancel, and we just get K, Q over R. So that's the voltage or the V field or the potential for a point charge. And you notice that for E field, it was KQ over R squared. For the potential, it was just KQ over R. Now don't forget, this is a scalar. So we don't have to, when we add, we don't have to worry about directions. So there you go. So that's the potential for a point charge, KQ over R. Now, if you have a positive charge, this is positive. If you have a negative charge, it's negative. That's perfectly okay. So I just said this. Let's say we have many, many point charges. Then the total V is just the sum of the individual ones, which is nice, right? No vectors. Okay, so here's our point charge. The potential is proportional to 1 over R. So two things. So these are concentric spheres. They're concentric with a point. So how many concentric spheres are there that have a different potential? Well, infinite, right? Infinite number. And you can see if R is small, this will be large. So this has a higher potential. If R is larger, then this is small. So if you're further away, this has a lower potential. And again, we see that the E field, perpendicular to the equipotential surface, goes from high potential to low potential. Okay, so here's a question for you. So everybody pause your video and answer it. All right, so the answer is 0. What's the sign of the work done by the electric force to move the charge along an equipotential surface? In other words, from here to here? 0. Because delta V, this is definition, delta V, delta U over Q, but delta U is minus W. Well, if it's an equipotential surface, this is 0. So this is 0. So that's 0. So everything's 0. All right? That's important. All right? The work done by the electrical force to move along an equipotential surface is 0. It's super important. So here's another question for you. So everybody pause your video and answer it, please. Okay, let's go over it. So 2 test charges, this one and this one, are brought separately from very far away into the vicinity of the big plus Q. First, this one is brought from infinity to point A, a distance r away. Then we remove this one and we bring this one, 2Q, and that's brought to a distance 2r from our big Q. So you're supposed to compare the electrostatic potential, this situation and this situation. So what's the answer? It's smaller, because here, okay, K, Q over R, right? We want to know the potential at this point. So the distance is R. At this point, the distance is 2R. So the potential here is twice as much as the potential there, just by using that formula. All right, here's a great question. So metal sphere 1 has a positive charge of 6 nanocoulombs. Metal sphere 2, which is twice the diameter of sphere 1, is initially uncharged. The spheres are then connected by a thin, long metal wire. what are the final charges of each sphere? All right, so pause your video and figure it out. Okay, let's talk about it. So the important concept here, so why did I ask those previous questions? Well, you know, come on, this is a conductor, this is a conductor, this is a conductor. So what's the work required for a charge to move here? 0, equipotential, right? Equal potential. So that means that the potentials will be the same. The potentials will be the same. All right, so we have KQ1 over R1 equals KQ2 over R2. But what's R2? R2 is 2R1. I'll just say 2R, okay? All right. Okay, so what does that mean? So get rid of the K's, get rid of the R's. So Q2 has to equal 2Q1. Now look, we only have 6 nanocoulombs to play with, right? So just figure it out. So basically Q1 is going to be 2 nanocoulombs, and Q2 is going to be twice that, 4 nanocoulombs. So we have a total of 6 nanocoulombs. All right, so the importance of this question is, some people think once they're connected by the wire that the charges are going to be the same. Wrong! Or maybe the charge density is going to be the same. Wrong! What's going to be the same is the potential. The potential of this one has to equal the potential of that one. So that's why that's why we wrote KQ1 over R1 equals KQ2 over R2. Okay. Now, you remember back in the E field chapter, first we learned the E field of a point charge, then we calculated the E field of multiple point charges, and you had to add vectors, and then we calculated the electric field of a continuous charge distribution, and that was a lot of nasty integrals. Well, guess what? We have to do the same thing for voltage. So this is nothing new. So the voltage of a point charge is KQ over R. So if we have a continuous charge distribution, then we're going to say that the point, we're going to call it a dq, and the voltage it creates is a dV. So we're going to just say dV equals K dq over R. So if we want the total voltage, we just sum the small ones. So the total voltage is the sum of the little guys, which is just K sum dq over R, integral dq over R. So that's how we're going to do it. Now again, don't forget, no vectors. So that's going to keep things simple. So here's a really wonderful example. So everybody read that or look at it carefully, please. Okay, so we want to calculate, it doesn't even say it, good golly. We want to calculate the potential right here. So we're given the charge, we're given the radius of this circle, we're given this distance z. All right, so here you go. So the voltage is K integral dV, right? Which is just K integral dq over R. Okay, ready? So first of all, what is R? What's the distance from the point to the dq? Well, it's right here, right? Pythagorean theorem, that squared plus that squared square root of. Now, is that going to change as we go around the circle? Is that going to change? No, it's not. So therefore, we can pull it out. Sorry, this is wrong. That K shouldn't have been there, sorry. Bad, right? Total voltage is the sum of the little guys. Good. All right, so the R, okay, let's do it like this. So K, so the R is constant. But look it, I want to write this in terms of the givens, you know, the Q or the R or the Z. So I'm going to write this. So we're going to have K over square root Z squared plus R squared. And then we just have integral dq. Well, what's integral dq? I mean, it just means, you know, we're summing up all these little q's. Well, what's the sum of a bunch of little charges? The total charge. Well, what's the total charge? Q. So we just have KQ over square root Z squared plus R squared. So what do you think of that? We didn't have to work with components. We didn't have to solve, substitute for dq. We didn't have to really do any integrating. So all I'm saying, it's not always necessary, it's not always necessary to do that. Sorry. Okay? Yeah. Because this is charge over length, yeah. All right, so we don't always have to substitute for that. So you gotta love these V field calculations. Okay, last example. Last example is a very, very important example to help you distinguish between electric potential energy and the potential. So everybody read that very, very carefully, please. Here we go. So we start out having these three charges infinitely far apart. And then we're going to bring them together, and we want to see what's going to happen to the electrical potential energy. Okay, when these three charges are infinitely far apart, there's no interaction. So what's the electrical potential energy? 0. Now, we have a positive 5, positive 6, and a minus 2. So you should just be able to see that because we have a plus 6 and a plus 5. They don't want to be brought together. Now this one certainly does, but just by the numbers, you can see that the potential energy is going to increase. It's going to be positive. All right, so let's see. What we want to do is, it doesn't matter the order, right? So what we're going to do is go out to infinity, grab one of these charges, and see what happens. And we'll just do it one at a time. Okay, so here we go. So we go out to infinity, and let's grab this one. And we put it at the, oh yeah. Okay, so we grab the 5 microcoulomb charge and we put it there. Does the potential energy change? Of course not. I mean, everything is still separated by infinity. Okay, but what happens? What does this charge create? A V field. Now, where do we want to know the V field? We want to know the V field here or there. So let's do it. All right, so this is for the plus 5. Okay, so at the corners of the triangle, using this equation, that 5 microcoulomb charge creates a V field. Let's just do it. 9 times 10 to the 9th Newton meter squared per coulomb squared. And the Q is 5 microcoulombs. And the distance is a half a meter. And that equals 9 times 10 to the 4th volts. So that means that this thing creates a V field. And at this distance, it's 9 times 10 to the 4th volts. Great. So now what are we going to do? Now we're going to go out to infinity, and we're going to grab, it doesn't matter the order, we're going to grab that 6 microcoulomb charge. We're going to put it there. Now, does it want to go there? I mean, this is plus, this is plus. Does it want to go there? No. So we're going to have to do some work, right? The potential energy is going to increase. How much? Well, there's a voltage there, right? This guy set up a voltage there. What's going to be the energy that this charge feels? Right there. Okay, so now we have the plus 6 microcoulomb charge, and it's going to, the energy of it is going to be QV. The Q is 6 times 10 to the minus 6 coulombs. The V is 9 times 10 to the 4th volts. 6 times 9, 54 times 10 minus 2, 0.54 joules, right? It's energy, joules, right? Okay. Ooh, I forgot to show you the thing. Sorry. All right. All right. So we have one more to go. But hold it. This guy created a V field. This guy also creates a V field, right? So these guys are both creating a V field. These charges are both creating a V field. Where do we want to know the V field? We want to know the V field right there. All right, so we want to know the total V field right there, because that's our last charge we have to bring in. So it's going to be, so the V field from here is going to be this guy plus that guy. So let's figure it out. So the V total is going to be just this, right? But, you know, from here and from here. So 9 times 10 to the 9th Newton meter squared per Coulomb squared. The R is the same, right? Half a meter, 0.5 meters. And then we have the 5 times 10 minus 6 coulombs from the top, and the 6 times 10 minus 6 coulombs from the bottom. When you add that up, you get 2 times 10 to the 5th. Right? Volts, right? Volts, because it's V field. So that means that right here, there's a potential, a V field, 2 times 10 to the 5th volts. Okay, one more charge. We go out to infinity, we grab that -2 and we stick it there. And it's very happy to be there, right? Because it sees all these positive charge. So we should expect the potential energy now to decrease because of that. Okay, there it is. So what's the potential energy? Well, there's a V field here. We just calculated. We want to know the energy. We're just going to use this again. So now we have that 2. So -2 microcoulombs. So the UE is -2 times 10 minus 6 coulombs. The V field, or the potential, is 2 times 10 to the 5th volts. I'm too lazy to figure it out on my own. I can do 2 times 2 is 4, yeah, 0.4. So it's minus 0.4 joules. All right, so when we had just these two, you know, the potential energy increased, but this decreased. So how do we get the total potential energy? So we're going to have to take this and add it to this. So we're just going to get 0.1. So, right, so UE total, again, this plus this, so it's 0.14. And again, you know, it's positive, just like we expected. And again, that potential energy, I mean, it's there because it takes work to put those charges there. So make sure you understand that problem. It's really important, especially to help you distinguish between potential energy and just potential. Okay, let's review. So we introduced potential energy, and we use it in conservation of energy problems. We defined the electrical potential. We found the potential of points, spheres, and parallel plate capacitors. We figured out how to find electric potential of continuous distribution of charges. We kind of skipped that. And again, electrical E fields are related to forces, so vectors. V fields are related to potential energy, scalars. Here's a definition of the electrical field. And if we have an electrical field, we put a charge in it. That's the force it's going to feel. This is the definition of V field potential energy, which is a scalar over the probe. If we have a V field set up and we put a charge in it, that's going to be the energy. And again, we don't have an electrical field meter, but we do have a voltmeter. And in lab, you're going to use this to figure out this. Okay, here's a review of the chapter. So potential scalar field created by electric charge, definition, I just said that. Energy conservation. If there's no friction, which there usually isn't for our situations here, we have kinetic energy plus electrical potential energy equals constant. So we're ignoring gravity. We're saying whatever we're dealing with is horizontal. The potential inside a capacitor, again, here's the definition. The potential energy is QES, so the Q's go away, so we get ES. So the potential depends on the position. It's all just position. The the V field of a point charge, again, here's the definition. The energy is K Q1, Q2 over R over the Q1 or whatever. The Q's go away, so we get KQ over R. So the voltage or the V field is proportional to 1 over R. Right? Position. And then how do we figure out the voltage of a continuous charge distribution? The total voltage is the sum of the little guys, and this is the voltage of a point, so we're just K integral dQ over R. And that's it for today. Thank you.